Hello, everybody. So we'll keep on our lectures concerning flavor physics. So yesterday I stopped in the middle of the discussion for the various constraints that you have on the Decay matrix. So I spent mostly my time to discuss how you could get information on the moduli of the various Decay matrix elements, always focusing on processes where you had a good understanding of the sources of theoretical uncertainties. And so that meant that in most of the cases, we were considering leptonic and semi-leptonic decays. And then that introduced a few hadronic parameters that we afterwards tried to constrain. So obviously, you use symmetries in order to get a first idea, a rough idea, still an idea of the value of the various form factors involved, for instance. But afterwards, and obviously I didn't spend time on that very much, you have to use more qualified tools in order to get accurate information. So for instance, numerical simulations like these QCDs, light consum rules and so on. And so that means that at this level, we had considered essentially constraints on VUD, VUS, VCG, VCS, VUB, VCB, and then remains the discussion that I alluded to last time, which is what to do with elements concerning the top. And so, so you can have for VTB, you can imagine to look at constraints coming from T to BW. So, and indeed you do have now constraints from colliders that are not very very strong in the sense that obviously when you look, as I said, the structure of the Decay matrix is highly hierarchical. And so when you look back at what I wrote concerning the Wolfenstein parametrization, VTB is very close to 1. So unless you see something which is very far away from 1, and then you know that you're really in troubles with the Decay matrix. But if you want to have relevant information that can be useful for the determination of the Decay matrix parameters, you would need a very high precision on VTB in order to be able to see very small deviations from 1 that are in the standard model, but which are indeed very tiny. So for the moment, that's useful as a cross-check, but not really as a tool to actually constrain for the Decay matrix determination. And then the problem is what to do with VTD and VTS. Why? Because you could say, oh, well, I look exactly at the same kind of transitions, but actually this kind of things is very challenging experimentally, because actually you're completely overwhelmed by the T to BW transitions. So that's something that you would have to be able to identify in the decay of a top the situations, very rare situations, where you have only jets with a total number that actually is with a strangest of 1, or only with up type and down type work. So that's very difficult to do experimentally. And so that's probably hopeless to try to use this way of determining VTD and VTS. So actually, the idea is to try to use other ways. So rather than trying to start from a T and see its decay into an S or a D, then you say, okay, I will try to look rather at transitions where you still have a transition between a T and a S, but that actually will be easier to handle experimentally. And so the idea is just to do the reverse, actually, to start from external states that will have an S or a D, and then to have the T inside the process as a loop. And so you come back to the question of looking rather at loop processes, and typically flavor changing neutral current processes. And actually, we already had this discussion when we considered this kind of diagram. I forgot to mention that typically this kind of so delta F equal 1 transitions. So there is all these kind of loop diagrams are known under the term, very highly technical terms of penguin diagrams, for reasons that have more to do with private jokes among physicists, theoretical physicists, than anything else. But that's how you encounter that in the literature. And so, as we discussed already once, in order to see how to analyze this kind of diagram, you see that actually you've got possible contributions from loop with any kind of up-type quark, and then you look at the kind of contributions that you have, and then you see that in the end you've got VUB, VUS star, for instance, VCB, VCS star, VTB, VGS star. And so in principle, by this kind of diagram, you have a handle on VTS that you don't have directly. The question is then to be sure that the hierarchy of the CK matrix elements is indeed able to help you to do that. And so you have to check. So here, for instance, you are with lambda square here. You've got lambda to the 4 here. And then you've got, so VCB, it's lambda squared again. So in principle, at least you've got some information concerning, if you're able to understand what's going on inside the loop, in principle, you do have the possibility to get information on this. I remind you that the analysis that we had last time showed that those contributions actually, the constant term that would come if you had a constant term independent of the mass of the top of the quark going through the loop is just cancelled by the unitarity of the CK matrix. And so we saw last time that actually the diagrams go like the mass of the quark in the loop over mw squared, which means that indeed, so due to unitarity, terms like this one survive, no constant term. And that means that because the top quark is the heaviest, then you really know that actually you're going to be dominated for this kind of diagrams by the contribution from VTB, VTS. And so that means that indeed we can try to use this kind of B to S gamma transitions dominated by top quark loops. And so that's good because you can hope to use the kind of separation of scales through the effective Hamiltonian that we already discussed. And so you can hope to actually separate the part that is really inside the loop, and that will be a short distance contribution from what's going on outside. And then the second thing is that that will be a constraint on VTS. And so you can think exactly like in the terms of what we did before concerning B to CL nu, B to UL nu, to either consider the situation where you do an inclusive computation, or to look at specific final states, so an exclusive determination. Okay, so B to excess gamma, so once again, that B going into whatever you want, but with a strangeness and a photon. So that's something that I already discussed very briefly when we were discussing B to CL nu, that actually you use the similar arguments related to quark hadron duality to compute the branching ratio. And as I said, you do have non-perturbative quantity matrix elements of your B that will be involved, exactly the same one as you have for sorry, I didn't say similar argument as B to XCL nu to compute the branching ratio. And once again, you have those matrix elements like mu pi, mu g, and so on, which are just matrix element of the B times or kinetic operators. Derivative operators, rather, I should say, actually, derivative operators. So those guys are the same, and actually what people are doing are combined determinations of those operators together between B to XCL nu and B to XS gamma. And you can also compute moments of the photon energy exactly like before. And that helps you to, by measuring those moments and those branching ratio together with B to XCL nu, in order to get at the same time the elements concerning the hadronic part, but also information on the Decay matrix. And actually the computation is now has reached quite a high level of accuracy. So you got the non-perturbative part here, plus perturbative part up to a high order now. So that means that actually B2 excess gamma is known to a very high accuracy currently, and so can be used in order to determine VTS in principle. B2 K star gamma, so you can't, so you need, when you're looking at B2S gamma, your photon is real, so you need a spin 1 meson at the end. You start from a spin 0 object, the B, so that means that you couldn't have B2K gamma, for instance, that wouldn't work. But B2K star gamma, you can have it, but then you start having, well, so it's the hadronic contributions are relatively well, challenging, let's put it that way. And actually, I'll come back to this when I'm discussing the anomaly. Actually, the anomalies, because actually B2S gamma is closely related to B2S LL, And so the problem that we will discuss for the evaluation of B2SLL concerning contributions, various contributions, will also be present for B2K star gamma. If you remember already some idea of what I was, the problem were already discussed a bit when I discussed the effective Hamiltonian. You remember I said that not all the time you could contract everything to a point. And then I actually took this kind of B2S gamma or B2S LL transition to illustrate the fact that you did have the possibility for some of the contributions, for instance, the top quark contribution, to shrink everything to a point. And so that means that you would, those kind of contributions, you would express them as with some coefficient times the matrix element that would be in the end of form factor. So the simpler case. But if you remember, I also drew a few diagrams where you had the possibility when you have a U or a C inside the loop, you couldn't shrink everything. You had to let propagate the up quark or the charm quark. And so that meant that in the end, you would have to take into account non-local contributions, and the evaluation of these non-local contributions is quite challenging and is also a question that occurs for B2S gamma when you're dealing with exclusive determinations. So all this to just say that I will defer the discussion of the issues when you're facing B2K star gamma to the general discussion of B2S LL transitions, and the same element will occur. So there is another possibility, and that will be one that will be also useful when we're discussing CP violation, because for the moment I was just discussing the moduli, so I'm not discussing the phases for the moment. And at some point I will have to discuss them. And so the possibility, actually, you can consider other flavor changing neutral currents, which are transitions that will have not a change by 1 unit of flavor, but by 2 units of flavor. And so that's diagrams that are actually delta B equal to, delta F equal to in general. And so typically these are so-called box diagrams. So for instance, one example of this kind of diagrams is you start with something that is, for instance, a B bar D. So it has a B quark and a D bar quark inside. And then you can use W exchanges to have up type quarks in the loops. And then the point is that you're not obliged to go back to the initial states. You can just, if you have an exchange with a second W, then the only requirement is that you do have the possibility of having the same kind of type of quarks at the end. And so what you have here is just the possibility, for instance, to say that you have a B and a D, but this time you change the B quark into a D quark and the D bar quark into a B bar quark. So that's the kind of loop diagram. That can actually turn B D bar into B bar D, or in other words, a B bar D meson into a B D meson. So you can change a neutral meson. You have mixing of a neutral meson into its antiparticle. And actually, you can play the same game as we did before for the delta F equal 1 case. So you can say, okay, if I try to look at the kind of CKM structure that I will have, actually, this time it's I have to take into account the fact that in principle, up and down, it's sorry. in the upper part and the lower part of the diagram, it's not necessarily the same up-type quark that is involved. So in principle, I can have different quarks running in the upper part and the lower part. And then you have something, a structure that will be, for instance, VQB star VQD, and then VQ prime B star VQ prime D. Here. Okay, and this is the matrix element with Q and Q prime as in the box. So I'm simplifying here. Obviously, you can have also, I didn't draw it, but you could imagine doing exactly the same thing, putting your W's here, and that would be the same kind of discussion. Okay, so and once again, so here you see that you have the same discussion of unitarity as before. So unitarity means of this CKM matrix implies that the constant terms, so terms, mass independent terms in this amplitude do not contribute to, so I didn't call it anything for the moment, to A, just because you will get the sum over all the possible product of the CKM matrix elements and leading to 0. And so that means that once again, we are dominated, we can do doing the expansion of AQQ prime in 1 over MW squared. Actually, you can check explicitly, but I gave you the argument that you have a contribution that scales since my pencil has some difficulties answering today. Okay. So AQQ prime is actually proportional to the product of the masses involved divided by MW squared. And so that means that once again, we are dominated by the top loops. So the only thing that I didn't recall, but that's important probably, that we're dominated by the top loops because of this, but also because when I'm looking at the various CKM factors that are involved, and we know already the answer, but I'm just giving you again the argument. If you look at the size in terms of the Wolfenstein parameters, they are all of the same size. Remember, that was one of the reasons we chose to use those products in order to build the unitarity triangle I mentioned last time. The idea was to have something which was not squashed, which had sides of a similar size, and indeed, that's exactly this BD meson triangle that we used. And I just recall that indeed the size involved that you see arising here when we're discussing the neutral meson mixing for the BD. So that's the connection that you have between the fact of calling that the BD meson triangle and this process. So you see that actually there is no suppression by the CKM factors. There is a suppression by the mass. So that means that in the end, this whole sum over all possible up-type quark inside the box, in the end, amount to just a single term. And so if you think in terms of a computation that would be more accurate and precise in terms of an effective Hamiltonian that we can build for delta F equal 2 processes, delta B equal 2 processes. So you have the transition between the B bar D and the BD caused by this delta F equal 2 effective Hamiltonian. And then the answer that you would get would be something that involves the square of the product of VTB and VTD. Then you would have something reminding you of the discussion we had concerning the masses. And then you had something which is just the actual external states that you had here, giving you the operator that you have to consider. And in this case, it's very simple. There is a single operator that you have to consider, because you have here, you got an interaction with the W, which is always for the left-handed part, and then you have twice the same operator in order to decrease by 2 units the flavor concerning the B quark, and to increase the number, the D quark number by the same amount. Okay, so that means that in principle, if we know something about this neutral meson mixing, which is allowed, I mean, the BD and the BD bar, they are neutral. They have the possibility to mix into each other through weak processes. Then, if you measure this, you've got in principle information on VTD here, as long as you have information on this matrix element, which contains all the hadronic information. So actually, that's, and the good point is that you see that the amount of difficulty that you have to compute this object is at least similar to what we had for form factors, because you have, once again, a single hadron incoming and outgoing. So that means that the tools that you have in order to deal with form factors, you can reuse them in principle for this. On top of that, you see that actually you have, it's a process that occurs, if you wish, at rest, because you don't have any injection of momentum. The BD and the BD bar are exactly the same object concerning the kinematics. So actually that means that lattice QCD is the tool for this, because it's like form factor at rest. And actually, indeed, this kind of computation has been a stable computation for lattice QCD that's been studied widely. And nowadays, there is a very high accuracy reached, not only for this one here, because here I'm in the standard model. So just as a commentary here. So in the standard model, there is a single operator contributing, but actually we have 5 operators in new physics in general. If you look at the kind of structures you can allow, and all of them are known now, have been computed using those same techniques, and are not to a quite high accuracy. Sometimes you have also so with a specific normalization, which is more historical than anything else. So those from those matrix elements are expressed. So they're often quoted using the term bag parameter, which is an old survivance of an old model for the connection between quarks and hadrons, the MIT model. So it's just a different normalization. So I will not discuss that in detail, but if you encounter the term, that just means in fancy units, this kind of matrix elements. The point now is so that I chose delta B, the BD transitions, BD bar mixing. So in principle, you can draw very similar diagrams for the other neutral mesons. And so once again, you will find, so for the other neutral mesons, so which one are there? You've got the BS. You will have the K0. So ST bar. Then you will have, well, okay, if I want to be reasonably consistent, since I started with this, okay, let's write it this way, BS, and then the D0, which is CU bar. So you can draw similar diagrams. Then the question is the interplay. So you do have, there is also mixing. Between the meson and the anti-meson. The question is whether the situation is as simple as for the BD, because you see that for the BD, the discussion we had was an interplay between two things: the question of the relative masses of the quarks inside the loop and the contributions coming from the CKM. So that we saw that there was a clear dominance coming from the masses because of the top quark, but we do have similar contributions from the CKM point of view. And so that means that we were able to single out the top quark contribution in the discussion of the BD transition. Now, the situation is not necessarily the same for the other cases. So if I'm just looking at, if you're just looking at BS, then you will have the same UCT quarks inside the loop. And then when you look at VT star B, VGS, VCB star, VCS, and VUB star, VUS, you've got lambda squared, lambda 4. So that means that you, in principle, you have a hierarchy which is compatible with the hierarchy that you would have from the empty M-top. So that means that in the end, this one is going to be the dominant one. So that means that for BS, top quark loops dominate. And so same discussion as before. So you just change the D with an S in the previous expressions here. And so that means that as well, BD mixing can give you an information on VTD in the same way we have hopes, and actually we are able to get information on VGS from BS bar mixing. So all that is well. Now the situation is a bit less well, satisfying for the Kern case, because here, so VTS, VTD, sorry. So VTS, VTD, VT, VC, okay, CS, VCD, and then VUS, VUD. And so now if you look at the values that you get lambda 5, lambda, lambda. So that means that here you're not at all in the same you're in a rather uncomfortable situation in the sense that you have exactly the opposite. You're suppressed by CKM when you're increasing in masses. So you've got a question of long distances, more complicated to handle. And then the last cases for the D0. So that's a different kind, because now you see that you don't have U, C, and T inside. I'm not writing it very well. You don't have U, C, and T in the loop. You do have here DSB inside the loop. So I should probably, for clarity, rewrite this. So D0 CU bar, and then I've got GSB or BS. So GSB. So I've got the mass of the B, the mass of the S, and the mass of the D. And then you've got the fact. So now we are doing a summation in a different way. VCB star VUB, for instance, VCS star VUS, and VCD star VUD. And so here you get something which is similar. So that's a bit of, again, there is a problem with long distances. And moreover, you've got the plus the fact that now, before we had at least the fact that we had M top squared over MW squared that was of order 1, and all the other ones are small. Here, you've got even MB squared over MW squared small. So the hierarchy from the mass point of view is really unclear. So it turns out, so that what is it telling you is that actually you will have to use different tools in order to address, in principle, K0 and D0, and there will be tools that are more on the hadronic side. So that means that if BD and BS, you can use really this kind of effective Hamiltonian decomposition in a straightforward way. For the Keon, you can use the fact that actually you have, it's a very low stage. You can have descriptions at the hadronic level through the interactions with pions that can help you in order to dispersive tools and so on. So you can try to use a hadronic description to supplement what you can achieve from the effective Hamiltonian decomposition. From the D0, then it's more complicated because you've got quite a large number of intermediate states. So a hadronic description is going to be very complicated because you will have to know the interaction concerning the final states in a very detailed way, which is not very much achievable. And so that means that actually the long distance are really complicated to estimate. So BDBS can be used. Keon, I'm not going to discuss very much how we do that in detail. I will allude to that at one moment concerning the kind of observables that can be interesting and that can be related to mixing. But for the moment, for D0, we don't have the way of exploiting that in a way that can be helpful for the determination of the CK matrix. It's also related, and you could guess that at some level, that so D0, okay, sorry, I said something, I was about to say something which was not correct, so I will just say that D0 is more used as, since it's in a very good approximation, a 2x2, so the big quark is playing a very limited role here. So that's probably better to try to see effects from can hope to see large effects from new physics in some models, because it's a way of probing boxes involving B-type quarks, whereas the rest is involving up-type quarks. So it's more something that is interesting for new physics in, well, boxes involving BSD, rather than not really for CKM determination. Okay, so one last point I did not mention is mixing for other states. So no mixing to consider for top quote-unquote hadrons, because obviously they decay before you have the time to hadronize. So it's not a question that you can formulate reasonably. The point here is that you can ask yourself if there is mixing between a particle and an untyped particle, if at least those outgoing states have reasonably long lifetime compared to the weak process that you're looking at. So if you have objects that are decaying too fast, then they don't constitute good candidates for external states. And so the process you're trying to probe, which is a weak process, which is a loop process, which is suppressed, it will never occur before you have the decay occurring. So the top hadrons, okay, that's clearly not decay too fast. And by that, I mean the top quark decays too fast. I mean, it's not that you don't have these kind of things. The second thing, which is probably a bit more interesting to discuss, is excited states, because in principle, what you have is, for instance, a B quark and an anti-S quark, or these kind of things. I focused on the spin zero, the lightest states that I can imagine, but I could imagine excited states. For instance, what about, I don't know, BS star, spin 1. You have things like D star 0, spin 1 also. But those ones, it's exactly the situation I discussed before. Actually, they're decaying strongly or electromagnetically. And so too fast compared to the typical scale of the mixing process. So once again, they are not good external states for the discussion. And that's different from the from BD, BS, D0 and K0, because those ones are decaying weakly. So same time scale, if you wish, as delta F equal to. But then the question is, at least it makes sense. Now the question is when you put the numbers, how it works. And so that's obviously a different question, but it's more a specific question of the specific CKM matrix masses involved. And so we can check whether this is true or not in general, but at least you can hope that there will be something interesting for those 4 guys mixing into their anti-meson, but certainly not for something which would be either an excited state, or something that goes to with a top quark. Okay, so now that we've got this, then the point is that since we can have these transitions between between a meson and an anti-meson, then you can have oscillations. So that means that you can look at the time evolution of your B meson and see whether it turns into a B bar, an anti-meson or not. So that's what is described as oscillations. And that's typically something that is also interesting also experimentally, because you can hope to produce this kind of meson, like the lightest mesons of with a given flavor, the given flavor of quantum numbers. And then you can start looking at their evolution and look afterwards. After a while, they will probably decay weakly again. And that will be interesting because that may give you information about the nature after evolution. So you can think already that experimentally, that's something that can be probed in principle. So we have to start looking at, so we have, so for this moment, I will just say M and M bar can mix due to weak delta F equal to FC and C, flavor changing neutral currents. And so that means that we have to look at the time evolution. So one thing is that we can say that when we're applying CP with a given momentum, then, I'm sorry, it's a bar, it's not a vector. And the same thing goes for how you turn, obviously, an anti-meson into a meson. So one thing that you have to be careful when you're discussing or you're reading the literature is that actually all these kind of discussions, you have very often hidden assumptions concerning phase conventions. For instance, here in general, I could say that the application of, I define my states so that the application of CP is not plus times the anti-meson. So meson is with CP is +1, the anti-meson, but that there is a phase. And that's possible because the phase in itself does not carry physical information. Then the question is whether you start assuming something at some level for this kind of phase conventions. In the end, when you're looking at something which is an experimental observable, obviously all the phase conventions will cancel and the result will be phase independent. But in the intermediate expressions, you will have different phase conventions. So you have to be careful when you're trying to take information from various papers in the literature. For instance, when you're starting to prepare a lecture, you might have different phase conventions that mean that at some point you have the impression that there are contradictory statements in the literature. Very often it's not a question of a mistake, it's actually just the fact that you're looking at something which is not an observable, and then that means that it's dependent on conventions that are sometimes stated or sometimes not. Okay, I'm closing the parenthesis, but it's just to highlight the fact that, especially for this kind of discussion, you have to be careful about this kind of conventions, phase conventions. Okay, so we have the mixing. So that means that actually, when we're looking at the mass eigenstates, there are linear combinations of M and M bar. So you can define them. So try to be consistent here. So PM minus QM bar. So P and Q are just complex numbers. The point is that you see that if you have, in the case that you have CP conservation, then you see that actually you will have the situation when you have P, for instance, P equals Q, equals a half, because then you have, and then you got a situation which is completely completely settled. But then in general, you have P and Q which have phases, and here the definition is that the mass of the light of L is supposed to be lower than the mass of the heavy. And the fact is that in general, they're not orthogonal states, which they would be in the situation where you have P equals Q. And so now that you have this, so you say I've got mass eigenstates, I can try to use this information in order to describe the time evolution of the system of M and M bar. So you can think of having, okay, so one way of dealing with this, which is customary, is to try to simplify the discussion, because you see that the thing that I've highlighted already is that you've got production at some moment, evolution, then certainly a decay at some point. And so in general, you would say, I need the whole theory in order to be able to describe all this. So the point is that it proves much easier to have a quantum mechanical description of this evolution. In any case, we are really interested in the time evolution, so that's a good candidate for a quantum mechanical description. So you try to look at the description where you're restricted to M and M bar. So it's a restriction to states, which mean M produced at t equals 0 and evolving. So that's the meaning of M of t. And the same thing goes for M bar. That's produced an M bar, that was an M bar state at the beginning, and then we let it evolve. And then you say, okay, I've got an evolution matrix for this. And I have something here in the middle. And then what I will say is just that I can write it as a 2x2 matrix. So up to now, no surprise. But the point is that actually this evolution matrix is not Hermitian. And why is it so? It's because you have restricted your system to M and M bar. But at some point, you have to take into account the states into which M and M bar decay. And so in this kind of situation, so if we had a situation where we consider not only M and M bar, but also all the possible final states of the decay, then we would have the evolution that would be something with an Hermitian matrix. And then we would have conservation of probability, meaning that in the end, you can follow the normalization that remains the same. Here, what's happening is that you cut your space because you want to focus just on M and M bar. And then that means that cutting, you have to take into account the fact that you're getting out of that system through the decays. That means that you don't have a conservation of probability. It means that, for instance, the normalization of your state will progressively decrease because of the decays, and this is taken into account through this non-Hermitian part of the evolution matrix. And so, so here, when I write this, actually, I've separated into two parts. Both of them are Hermitian. M is Hermitian, gamma is Hermitian, but you see that here you've got an I, that is the introduction of an imaginary part. So if a few elements in this description, so if you write this evolution matrix, so what is important for us are the off-diagonal matrix elements. The diagonal matrix elements, it's just the propagation, the evolution. I'm staying inside the same, I've started from an M and I stay as an M. And then, so you have, you can see that actually those of matrix elements that can be expressed in terms of very easily in terms of this so you can separate the real and imaginary part, so, or in other words, what is called dispersive part and absorptive part. The idea being that through the gammas you're actually evading from the two component system that you wrote. Okay, I'm not going to spend too much time on properties of this, but just you do have actually a few properties for this metrics that are important. Actually, you can show that, so we're breaking CP, we are not breaking CPT. The CPT theorem is sufficiently important for us not to have troubles with it. And actually, when you're applying CPT and looking at the matrix elements, when you're staying from M and going into M, and so on, you can show actually that by applying CPT, you can connect the matrix element for the transition for where you stay from M to M and M bar to M bar. And that means that actually you need to have the same value for the M11 and M22, sorry, and the gamma 11 and the gamma 22 entries. Then so, and those M11 and M22 terms, actually, you see that conceptually they're corresponding to the evolution under the, they're dominated by a question related to the strong interaction. Then the part which is giving you a headache, which is the part coming from the off-diagonal terms, and also gamma in general, not only gamma 1, 2, but also gamma 1, 1 and gamma 2, 2, because they're corresponding also to decay through the weak interaction. I told you that we're considering states that are decaying also through weak interaction, that mixing through weak interaction, decaying. So all that is related to weak interaction. So you can imagine that those guys will be small corrections to what is given by M11, M12, M22. Okay, so that's just to give you an idea of the physical content of this. And so you can, obviously, if you want to describe more easily the evolution, that's not very complicated. You try to diagonalize the matrix evolution that will give you the states that are actually of interest for the time evolution. So this is something diagonalizing the matrix, the evolution matrix. Then you can solve the system. And then that means that so you can say something quite simple. You can say that actually the evolution is given by the time evolution that you expect for the two states that have been identified. Up to a matrix that is mixing the two components, and actually that is related to the P and Q terms that I introduced at the beginning. Okay, and so here you've got the left mass and width, not the left, the light mass, the mass of the width of the light meson as well as the heavy meson. So that's reminding you of the two mass eigenstates I just introduced at the beginning, and you can actually express the masses and the width. So you have an average mass and an average width between the heavy and the light state, and you can show that actually they're connected to the diagonal terms. Well, you could imagine that, because if you removed any kind of perturbation, that's what you would expect in general. And then you have a difference of mass, which by construction, since we said the H is heavy, this one is positive. The difference of width can be either positive or negative in general. And here we chose a convention. So in practice, for the state we're considering and for the standard model, this one is defined as positive or 0, actually, because for the BG it's very small, so small that it's not observed. Okay, so once you do that, you can express in a slightly more practical way the time evolution. G minus. And so you've got two functions that are present, which correspond to the probability of staying in a state and to moving to the anti-state. There is somebody with a mic on. It's not that I don't want to hear you, but it's making some noise here. So you have a structure which is not very simple, but not very complicated either, which is in terms of trigonometric functions involving the difference of masses and the difference of width. With the fact that at 0, one is 1 and the other one is 0, which is exactly what you would expect, because you start from the state and then you decay. And then you can relate finally the components of your various of your linear combinations. So you can show that P over Q squared is actually given to you by the off-diagonal matrix elements. And so in the situation where gamma 1, 2 is much smaller than M12, actually, it becomes just this, so it's a pure phase. And actually, it turns out that it's a very good approximation for BD and BS, as well as for K, actually. And so what you have in the end, when you do the algebra, is that, for instance, for BQ, so Q equal D or S, this ratio is just VTB star VTQ, VTB VTQ star. It's just related to the exponential of the product of matrix elements. So that means that actually you can, if you have a way of measuring the mixing and you see that this mixing involves Q over P, you could have in principle information about phases that are present inside the CK matrix and that are potentially related to CP violation. So for instance, for BD, Q over P will be related to one of the angles of my triangle.
Sébastien?
Yes?
So, sorry to interrupt you. I mean, if you want, when you think your radio is in good time, you can also make a break if you like, if you want.
Pardon, I didn't hear you properly.
No, I just wanted to mention that if you like, you can have a break whenever you feel.
Yeah, sure.
Yeah.
Actually, that's a very good point because I was about to make it. So excellent. So yes. So the final comment that I wanted to make before the break, because I think that's useful, is actually that if you think in terms of, so you see that M12 and gamma 12 are playing an important role, obviously, for mixing. So both of them are related to the presence, this kind of boxes that you have. And so, as I said, you've got UCT inside, in principle. But here, M12 is actually the real part, so to speak. And so that means that, as we discussed already, that's going to be essentially dominated by the top quark. Whereas for gamma 12, that corresponds more to an imaginary part. And so in that case, as we discussed already a few lectures ago, these kind of imaginary terms, they do come from the fact that you can insert intermediate physical states because of the unitarity of the S matrix. And so that means that for those ones, actually, you need to have, so it's dominated actually by states with a charm mesons. Whereas for top quark, it's dominated by virtual intermediate states. So just to say that the physics that is involved in both cases is quite different. So so that's something, that's point I wanted to make here. Okay, so I think indeed, as proposed by Fabio, we can make a break, 10 minutes, and then keep on with coming to the observations that we can make through this mixing measure. So just one thing, maybe that just to make the point home, the fact that delta M, which is related actually to 2M12, it's actually exactly the box diagram that we looked at before. So it's really a way of getting information on the value of these matrix elements. So this way you've got, by measuring the difference of masses, you do have information on VTD and VTS. If you're looking at BD bar mass difference or BS bar mass difference, as long as you know these back parameters. And so that's the way forward in order to get access on VTD, VTS when you're discussing the CK matrix. Okay, I'm not going to, well, I will skip the part concerning kaons because otherwise I will not have the time to finish properly. As I said before, when we were discussing this time evolution through mixing, you have, because I just wrote it, information on seems that my connection is a bit whimsical today. Sorry about that. What's happening? Sorry.
Sébastien, is there a problem? No.
Well, it seems that for some reason, when I start trying to share, it stops. So I will try again and see whether that works. Okay, that seems to work now. Sorry. Okay, so this time evolution for neutral meson mixing. So you see that you have through delta MD, delta MS, so that corresponds to delta M for BD and BS. You have information on VTD and VTS. But as we discussed, you saw also appearing this quantity Q over P, which is related to the linear combinations involved when you're talking the connection, making the connection between the CP eigenstates and the mass eigenstates. And we saw that actually there is a phase that is accessible this way. So when I say that, I didn't say much. I'm just saying there is a phase which is something that we can think of using. Now the question is how in practice we can use it. But that brings back to the question of how we deal with the CP violating part of the CK matrix, because up to now, I spent all my time discussing how I could have information concerning CK matrix elements, but I never used the fact that there was CP violation in the game. And so, especially when we're discussing the angles of the unitarity metric, of the unitarity triangles, I remind you that the fact that you've got this unitary triangle with rho bar, eta bar, you rescale the BD triangle. You have the three angles that were present here, and the fact that they are different from 0 and pi is related to the presence of CP violation. So we have not used it at all. So we can think of trying to use that. And so actually, you can, because of the situation that we have, as we said, a weak interaction. So in potentially CP violation in mixing and in decay. So in principle, you can think of building observables that will probe CP violation in mixing, in decay, plus another possibility is that you can try to make an interference between the CP violating effects present in mixing and decay, because in principle, these are phases. You might try to probe them through CP violation mixing, you can try to probe them through CP violation decay, but since we do have mixing before decay, you can imagine also make an interference between mixing and decay in order to get information. And actually, that's the kind of things that you can use. And so I'm going to go very briefly between the these three ways of probing CP violation. So CP violation in mixing is exactly looking at this Q over P, and more specifically at the phase that is present in it. So typically you look at, for instance, BD and BD bar. So they will evolve. You start from BD, BD bar, and so on. And then the idea is that you look at the evolution of, for instance, BD into BD bar, and then you look, oh gosh, what's going on?
Is there a problem, or
Well, it's
you are still co-host, so you should be able to.
yes, no, it's the problem is not on your side, it's on my side. Is that for some reason suddenly my iPad decides that he doesn't want to broadcast anymore, and I don't know why. So it stops broadcasting, and then you don't see anything, obviously, but it's on my side. Okay, sorry about that. So, for instance, you look at the evolution from a BD into a BD bar, and then you choose a final state. So I remind you that this is the content that you have is a B bar D going to BD bar for the week, interaction boxes, and then you decay into something that will actually tell you, so a semi-electronic decay, so that you know that actually this comes from a BD bar, a B bar D, sorry. So because it's connected to so B2C transitions that will tell you that in the end, so anything would go, that is going to tell you what is the actual flavor, whether it's a B or a B bar. And you can look exactly at the opposite process, where this time you go from a B bar to a BD, and then you look at a semi-electronic process where the charge is also telling you that what kind of processes is inside. So, or what kind of quark initiated this. And so you can build an asymmetry, a semi-electronic asymmetry, that is just checking whether the probability of these two decay chains is the same or not. And in principle, if you don't have CP violation, you would say that it's possible to do this in both directions without any difference. And so that's exactly what I'm writing now. So you take the difference between the two decay chains divided by the sum. And if you look back to what we just wrote, you see that when you look, you go from, so this is probing the fact that you're going from B bar to B or from BD to BD bar. And then that's each time you have a change of this, then you have a Q over P in one case. Let me try to find that again. Here, you see that you have a P over Q here and a Q over P here. So that means that, and so this is at the level of the amplitudes, and then you take the square. So that means that in the end, when you're writing down what's going on, you will end up with something which will be involving Q over P to the fourth. You've got Q over P to the square on one side, P over Q to the square on the other side, and then when you're normalizing, you get Q to the P to the fourth. And so this, so here you see that this will be, there will be CP violation, but that will occur if Q over P is not a pure phase. So as I said before, in the case of BD and BS, it is a pure phase, but you could imagine, oh, it is a pure phase. It's very close to be a pure phase, more exactly. But in principle, you can use this to constrain the size of higher order effects that would make this not being a pure phase. And in particular, you can think now, we're switching back and forth between standard model and new physics. All I'm saying for the analysis of the matrix elements is in terms of the standard model, but think in terms of new physics, you would have an additional contribution coming from loops involving other particles, and those ones are not necessarily going to contribute with the same weak phase. And so in the end, you will have something, a contribution to Q over P, which will make the standard model value, a pure phase, shift and maybe not be a pure phase. So that's an interesting constraint for new physics. The second possibility is CP violation in decay. So that's probably the one that would be the most natural. So here, for simplicity, so just to the complications of mixing, in principle, you could think of doing the same, but I will do the same with a neutral meson afterwards. But imagine that you've got a B plus this time going into a state, final state, whatever it is, and you're comparing this decay rate with the probability of a B minus going to the CP conjugate state. And so you can, for the moment, I'm just writing a tautology. I'm just saying that I can evaluate that if I have a knowledge about the corresponding amplitudes. So typically that would be a B plus effective Hamiltonian and F plus, and I've got the opposite situation here. So I can write down this as A F plus and A bar F minus, or so I can write B plus or B minus or B and B bar. That would be the same thing here. Okay, so at that stage, I didn't say anything. I just said that I need to have this the moduli of those two amplitudes to be different from each other in order to have something that would be CP violation decay. So now the question is whether we can say a bit more. And so the idea is just to say that in general, what we expect is that the decay will be triggered by several different diagrams or contributions. And so that means that in general, I will be able to separate or to say that I've got several amplitudes contributing and potentially interfering. And with each time a modulus. And then there are two phases. And once again, we come back to what we discussed already, the fact that you have a part which is, when you look at the phases that are present in an amplitude, part of it is related to strong dynamics, rescattering between, for instance, final states. Exactly the reason why we had, if we increased enough Q square, we had an imaginary part for some of the form factors we're considering. And so this is due to strong dynamics, rescattering between the final states. But we do also have a part which are weak phases, which are the phases that comes from, in the standard manner, the CK matrix, and that we discussed at the first lecture, that actually when we're using CP, we're going to take the complex conjugate of the CK matrix to look at the CP conjugate process. So that means that when we do this separation, having in mind in the standard model where they come from, but the name strong and weak, in principle, you could use that for anything that is CP even and CP odd. So even in the presence of new physics, you could imagine doing this kind of separation. Then you will have that the CP conjugate is going to have this kind of structure. And so, for instance, if I'm assuming that I've got two amplitudes only contributing, and generally we try to find processes where, to a good approximation, this is true, then you do, and you assume, for instance, that A1 is much larger than A2. Then in the end, you can show very quickly that this asymmetry that I wrote at the beginning is actually going to be given by this. So the ratio of the two amplitudes, the moduli this time, and then the product of the sign of the difference of phases, the strong part and the weak part. So that's telling you that actually you need to have different strong and weak phases contributing to get CP violation decay. And moreover, the second point is that if we want to interpret this kind of asymmetry, we need information on the strong dynamics involved. In other words, you have in A2 and A1, you've got information on the moduli, you got information on the moduli of the CKM matrix element. If we want to have information on phi 1 and phi 2, we need to know something about delta 1, delta 2. And so that means, once again, that we need to know something about the strong dynamics in order to be able to extract out of F plus some information on the weak phase. So in some cases, and I will briefly comment on that at the end, it is possible, but it's not the most general case. So, and that's a point which maybe I can emphasize again, is that you do have quite a lot of measurements of this kind. So measurements of CP violation of this kind at more than 5 sigma, actually, for instance, k on into 2 pions, b0 into pi plus pi minus, b plus to dk plus, b0 bar to pi k minus pi plus, sorry, k minus pi plus. So the question, so you do have statements that there is CP violation, so it's not a problem in itself. But the fact is that if you want afterwards to use this in order to quantify what the CK matrix element, it's much harder. So, and that's a problem that we will face later on when we're discussing the breaking of latent flavor universality. So that's the same problem. You've got a symmetry that is broken, so you can build observables to show that it's broken. So that's not a problem. But then if you want to assess precisely the parameters describing this breaking, it's a different story, because being different from 0 and extracting out of that a specific value for the parameters involved is not exactly the same thing. So not to say that these kind of measurements are not important, they are. I'm just saying that you have to be careful that they cannot all be used in order to do some kind of metrics of the metrology of the CKM matrix parameters. Okay, and the last, so we had, as I said before, we had here CP violation in decay, we had CP violation in mixing. Then I suggested that we can try to look at CP violation in the interference, mixing, and decay. And so that's back to the story I just told you at the beginning, is to say, okay, I can try to, so I have the production of a meson or an anti-meson, and they're evolving, and after a while they decay. For the interference to occur, they must decay into the same thing. So the story we have is just that you have, for instance, a BD and a BD bar evolving into each other, and then they have the possibility of decaying. And for this to make sense, it has to be a CP eigenstate as a final state. And so you can build an asymmetry that will actually be a combination of the two previous cases. So you start with a given B or B bar, and then you let evolve and decay. And you look at the time dependence of this object. And so, not very surprisingly, you will start having the mass difference occur. You will have also the difference of width to arise with different cosine and sine for delta MD, hyperbolic cosine and sine for delta gamma. And then you have coefficients in the front that arise. So you've got A dir, A mix, and A delta gamma. So just here, the denominator is equal to 1 if you are in the case where there is no noticeable difference of width between the two states. That's the case for BD. So that's why in the BD case, generally you do find only two coefficients being quoted. And actually, so I'm not doing the computation here, but taking the evolution that we've just discussed before for BD into BD bar and the other way around, then you can express actually all the three coefficients that you have before in terms of a single quantity lambda. Which is actually quantifying exactly the interference between decay and mixing, because that corresponds. So you've got the mixing here, the decay, and you see that at least a mix, so this one, is sensitive to the presence of an imaginary part in lambda. So the fact that you do have a phase, a relative phase between the mixing and the decay. And actually here, you can actually, so here you see that you've got the amplitude. So A bar F is just the amplitude where you start from a B bar and you go into an F. AF is the same when you go from a B to an F. Actually, it can be interesting when we're discussing the CP violation to introduce A bar over F bar. So that's actually the one that you obtain once you're applying CP to AF, because when you're applying CP, you have to apply it to B, to the effective Hamiltonian, and to the final state. And the fact is that because we chose FCP, that means that actually that's going to be eta CP, well, eta of F, so the CP parity of the state. CP parity times F times B. So that means that this one is actually eta F of F bar F. So just to explain, the point is that when you're doing CP, that's very easy because you just take all the weak faces to their opposite, and that's it. So you know, if you have the expression of AF, you know the expression of A bar, F bar. And then since in the end, what you're interested in is a state which is a CP eigenstate, you can re-express that in terms of the quantity you would naturally, more naturally come to terms with, which is B bar going to F with it. And so that's why you got these two expressions, one which is more natural phenomenologically, one which is more natural when you want to connect the expression, the theoretical expression of AF with something, a bar F, a bar actually, with the theoretical expression of AF, because you just have this taking the weak faces to their opposite to apply, which is much easier. Okay, and then if AF is dominated by a single contribution this time, remember last time when we were discussing CP violation in decay, we said we need at least 2 different contributions with 2 different weak faces and 2 different strong faces in order to get something interesting. Here, that's the opposite. Actually, what we are after is much more something where we are dominated by a single contribution. So if we have the same kind of separation for AF, so this decay amplitude from B to F, and separate into the strong and the weak phase, then what you have will be Q over P exponential minus 2I phi eta FCP, because A bar, F bar is going to be eta F A I delta A minus I phi. And you got the ratio of these 2 guys that give you exponential minus 2I phi. Here, as we said, it's a pure phase, at least for BD and BS. So if I'm saying that it's, for instance, something that I call phi B, then you see that eta F, you got eta F phi plus phi B. And then eta FCP, the time evolution of this guy is going to be very simple. That's going to be related to delta MT times the imaginary part of lambda. So you will have a sign component which will correspond to, eta eta F sine of 2 phi B plus phi. So that means that actually, in this case, you have the possibility of having something which does not involve anything but the weak part. How is it possible? It's just that all the strong part here is the same for the 2 amplitudes, and so it cancels in the ratio. And because we're doing an asymmetry that is not just an asymmetry involving the decay amplitudes, but the interference with something else, which is the mixing, we are able to build an asymmetry that cancels the strong part, but still carries some information on the weak part. That's the interest of this kind of asymmetry and this kind of measurement. And so in practice, and so that's going to be the last part I'm going to discuss very briefly. And just for fun, I show a few plots so that at least you see something out of all this discussion. So one thing which can be done is to look, and that used to be a very important decay at the time we were discussing the beginning of the determination of the CK matrix. It's a BD to J psi K short. So what is that? It's, you start with a BD, then you're producing a CC bar pair, which is the J psi state, so CC bar spin 1 state. And then you've got an S quark that go into your K short. So that's the K short is a mixture of K0 and K0 bar. So by doing this, you are able to access K short, which is the state you're identifying. But then you do have also, so that's one thing that you have, but you can have also different diagrams for the upper part, and I'm just showing those ones. So I can also have terms where I have, again, those kind of penguin contributions, where I'm closing the loop, I'm doing a loop, and then I can have, in principle, So that can be a photon, a Z or a photon Z or gluon, sorry. And then I can have up-type quarks here. And so I'm going to make the distinction or the discussion between the case where you got C or T here, or you've got the U. Why do I do that? Because when I'm looking at the kind of contribution that I have, so here it's a tree contribution. You don't have any kind of loop. You just have a W exchange. VCB, VCS star is involved when you're looking at the CKM factor. That's a real contribution actually. And when you're counting, it goes like O of lambda squared. Then if you're looking at the penguin contributions, so C, T, or U, then VCB, VCS star, or VTS, VTB, VTS star. So VCB, VCS star, that's the same contribution as the tree case. VTB, VTS star, it's very similar because actually by unitarity, you see that you can express as the sum of the two other terms here. One of them, which is dominant, and the other one, which is very small. So actually up to a small correction, those two contributions do have the same CKM factor as the tree contribution. And the last one has a different contribution, but it's a penguin. So it's suppressed by a loop, and it's also CKM suppressed. So what you say that to a very good approximation, you are in the situation where this is dominated by a single weak phase. And so that means that in the end, when you're looking at the actual, so this is real. So you do the interference between something which is real and then Q over P, so the mixing phase. So it's not really a surprise that in the end, you will get sine to beta, because here, as I showed before, you've got a contribution that comes from Q over P, which is in the case of the BD meson to beta. And then the contribution, there is no phase for the weak phase for the amplitudes here. So in the end, you get something which is a measurement on sine to beta. In principle, and I'm not going to spend time on that, you can do the same for BS. So that's the same kind of diagram, but you have here an spectator is quark. So that's why you end up with BS, J psi, and phi. You will get, in principle, an information on the BS mixing angle. You can show that, once again, you're dominated by a single phase and so on. The point is that the corresponding angle is actually very small. So it's the same kind of definition as for beta, because that's the same physics, but you're replacing the D by S's. And you can show that actually that's in Wolfenstein parameterization, it's going like lambda to the square. So that's very small. So that's challenging because you're trying to find the sign of a very small object, and that's going to give you the time dependence of this asymmetry. The second difficulty is that phi is a spin 1 meson. So actually, and J psi is also spin 1 meson. So that means that actually you've got several helicity configurations. That you start from a pseudo-scalar object, but you go into two spin 1 objects. So that means that you can have different helicity configurations with different CP properties. And you saw that when we were discussing this lambda ratio that was related, giving you information on the angles, we had at some point to use the CP properties of the final states. So that means that we have to separate by angular analysis the various helicity components. And that's challenging. In the case of BD to J psi K-shot, J psi is spin 1, K-shot is spin 0, so the helicity is completely fixed. You don't have any choice in what's going on. It's a P wave, and that's it. So that's another difficulty that makes the measurement challenging, but it can be done. Okay, I will be very short for the two other possibilities. So just to say that you have the possibility to use B to decay in order to measure gamma. So the idea is that you're looking this time at the interference between tree-level transitions. So you have, for instance, this one, and then you've got this, oh no, sorry, I'm just doing twice the same one. Okay. So you've got another diagram that can contribute. So with the same charge particles, but as you can see, there is a difference in the neutral d meson that is involved. You've got, in one case, something going like a lambda to the cube. The other one, because you've shifted the connections through the weak, the W boson, is VUB, VCS star rather than VCB, VUS star. And that means that in principle, you do have a sensitivity to the phase of VUB if you're able to make an interference of these two diagrams. And that's possible if you choose, it's possible if you choose the a final state into which both D0 and D0 bar can decay. And that's possible. So I'm not going to spend time on that, but it's possible. The last one I wanted to advertise is that you can also look at decay. So that's an interference between decays here. B2 pi pi, that's involving both CP violation in decay and in interference. The idea is that you gather information on the strong dynamics of the decay by looking at all the possible decays that you can think of. So B0D, BD, B plus to pi plus pi 0, and B0D to pi plus pi minus. And actually to use isospin to relate the strong dynamics involved in the various channels. So you measure as much as possible concerning all these various decay rates. So you do have direct, well, CP violation in decay. So for instance, B plus to pi 0 compared to B minus pi 0. then when you have the B0, BD, you can look at the time evolution, how it can mix. You have interference between the mixing and the decay into, for instance, pi0, pi0, or pi plus, pi minus. So you've got quite a large set of different observables. You describe them using information on the strong phase, on the strong part and the weak part. The strong part is correlated, linked between the various modes because of isospin. So you can reduce to a very short number of strong amplitudes. So that helps you afterwards to have a constrained set and have as many unknown as observables and to get information on this. And in the end, you get information on sign to alpha, this time from this. So I can, if you wish, later expand on this. Okay, so before letting you go for lunch, I just wanted at least to show you a few illustrations of that. That's going to be just pictures now, essentially, but I think they're quite telling. So let me see, yes. Okay, so that's extracted from the latest presentation last year at the CKM conference from a group I belong to, which is actually doing this kind of assessment of the CKM metrics using both theoretical and experimental inputs. And so that's the plot that you typically obtain in the end. So this is the unitarity triangle I just discussed at the beginning, the BD unitarity triangle. It allows you to see the situation for rho bar and eta bar. You don't have on this plot A and lambda, but obviously when you determine the 4 parameters, you determine them all together. And what you have here is the apex, which is here. So that's the position of rho bar and eta bar. You do have various constraints coming from various contributions that we discussed that are all giving you constraints on the value of rho bar and eta bar, and also on A and lambda, obviously. And so those various bands with colors correspond to different constraints that you get. And for instance, you've got here delta MD and delta MS that are present, that come from the measurements we discussed before on BD and BS. You do have sine to beta that I just discussed, gamma, alpha, and information on VUB that is actually doing the combination of the various methods I presented, and even some that I didn't present, actually. I forgot to mention that you can also measure VUB through electronic decays of the B meson, so that's something that I should add. And so just to show a zoom of the situation, and so that's showing you a bit the complexity of the situation for VUB. You've got several different determinations that are allowed here. Semi-electronic that I discussed mainly, electronic, and also some measurements that come not from B, but BS and lambda B, semi-electronic again. You see that there is quite a good overlap globally between all the various constraints. And so the game that was played very often was to separate in those measurements the ones that are actually a measurement of CP violation, so measurements of the angles, compared to what I discussed during the previous lecture, which was more the sides, and so the moduli, so that's CP conserving, because you would have those processes occurring even in the presence of CP conservation. And then you can also think in terms of tree versus loop. So when you have on one side all the semi-electronic decays, but also gamma, because I told you it was related to the interference between tree decays, whereas other processes that involve loops because they involve mixing in particular. And so you have the box diagrams that are present and that can be potentially more affected by new physics. Okay, and then the thing that I didn't discuss very much, but in principle, I said you've got 6 different unitarity relations. So in principle, 6 unitarity triangles. I discussed a bit briefly at the beginning of the previous lecture, the fact that you had 4 of them, 4 relations that could be of interest in relation to the mixing for BD, BS, D, and K. But actually, you can show those triangles The point is that they don't look very much like triangles because in each cases, we are focusing only on the small side of the triangle. For instance, for the BS, you would have the large, the other apex of the triangle be at 0.1. So that would be very far away here because you see it's from 0 to 0.1 for rho bar here. So these are rho bar and eta bar defined for those triangles. They're different from the rho bar and eta bar that we define for the usual unitarity triangles, but you can recast all those constraints in terms of constraints for the parameters describing those other unitarity triangles. And you see the consistency is present in all cases, showing that there is a good agreement of all the constraints that we use in with the CKM picture of CP violation, which is quite comforting in the end, because if we had spent 2 lectures on something that doesn't work at all, that would have been probably quite frustrating for both you and me. Okay, I think I will stop here. Thank you very much for your attention.